Hi guys. You already know that I'm traveling on Monday, so here's the lecture we promised we're going to do online. And in this lecture, we're going to focus on talking about the joint probability distributions, the marginal distributions from that, as well as independence. You'll see what that means. But what we discussed before are we already discussed different distributions already, right? But those distributions usually have one random variable, right? But here from today, we're going to talk about a distribution. We call it joint probability distribution that actually have multiple random variables. Surely we start from 2. So let's say if here's what is a joint probability distribution, right? Let p, x, and y be a joint probability mass function. Then we sum all of them together on x and on y, all the probability together that give us 1. This is very similar to what we talked before, right? For, you know, probability distribution with one random variable, we sum all of the probability together, that's equals to 1. So here is the same, right? And similarly, the probability of x and y is bigger or equal to 0. Still, it cannot be smaller than 0, right? Of course, when we talk about a mass function, then you know that this is discrete random variable, right? So that only discrete random variable has mass function. So we know the mass function. Then let A be an event consisting of x and y pairs. Then the probability of event A just equals to all the probabilities of each pair belong to event A. We sum them up, and that gives us the probability A, right? So it's pretty similar to what we have before. Before, maybe we have Px and x belong to A, or Py, right? Y belong to A. Now we sum them all together. That gives us all of them together, right? Basically, we just for both random variable, we need to sum them together. So pretty similar. Here's one example. If that is a bit hard to understand, maybe this example will make you understand this a little bit better. So I have two random variables, right? They're discrete, apparently. X is the amount of auto insurance policy, right? Amount of auto insurance policy. Maybe for a household, I can choose from this two, right? And Y is the amount of home insurance. So there are 3 policies. You can choose 0, so don't buy any policy, maybe 100 or 200, right? And then the joint probability of X and Y is basically the probability of, capital X equal to lowercase x and the capital Y equals to lowercase y, right? So you can think this. Now, here's a table shows the probability, the joint probability, right? You can think this as, let's say, when x equals to 100 here, and y equals to 0, so basically this is 20, right? 0.2, sorry, 20%. That means 20% of population bought the car insurance policy, which equals to $100 per month, and then didn't pay for anything for home insurance, right? So this is 20% of population. Then in this way, then this basically 5% of all the population bought a car insurance and pay $250 per month and still get nothing for house insurance, right? The same, then same here, this basically means 10% of population spend $100 on auto insurance and spend another $100 on the home insurance, right? So that's basically what it means. Now, here comes the question, right? What is the probability x equals to 100? And then what is probability y equals to 200, right? you can pause the video and think a little bit to see what you think a little bit, and then think what would be the result. Okay, I hope you have already spent a little time think about it. So basically, okay, we actually missed one corner here, but doesn't change anything, right? So basically, if we want to find out px equal to 100, we don't really care what y is, right? We actually need to count all of them, right? So y can be equals to 0, can be equal to 100, and can be equal to 200. As long as x is equal to 100, that's fine. We just add them all together, right? So basically, we're looking at this row here. This is px equal to 100. We add 0.2 plus 0.1 plus 0.2. Let's give us 0.5. So 50% of chance, right? So that's px equal to 100. And similarly, we can calculate y, right? Py equals to 200, which same here, right? We need to consider all the situations for x equal to 100 or and equals to 250. That's give us 0.2 plus 0.3 together give us 0.5, 50% of chance, right? So we can calculate both of them relatively easily. But this, basically shows us what is we call the marginal probability mass function, right? Marginal probability mass function. So the marginal probability mass function of x and of y can be denoted by p x x and p capital Y lowercase y, right? They're given basically like this, right? So here we are trying to calculate the marginal probability function of x denoted by this, which basically equals to, we control the x, but add all the values for y together, right? That's how we get the marginal probability mass function of x. And same here, if we are trying to calculate the marginal probability mass function for y, it's the same thing, right? We control y, this y value is determined, right? We need to find that. But we can, but then we just add all the x together. Right? So that's give us marginal probability of y. All right. So that's basically what we did, right? Find the marginal probability mass function of x and y for all the joint distributions, right? So let's find x first, right? X is basically we have two values, right? For x, we have two values. One is x equals to 100. The other is x equals to 250. Now, we can just add them together. So you see for this mass function for x, right? X equal to 100, and basically this row, we already calculated that equals 0.5. So 0.5. And when x equals to 250, then we add this row together, right? This 0.05 plus 0.15 plus 0.3. Add them all together, give us 0.5 as well, right? There's no other values anymore, so 0 otherwise. So that's marginal probability mass function for x. Similarly, we can find for y. Y have three values, right? So we have 0, 100, and 200. And then we basically add each column here together, and then we find the marginal probability for y with different values. So when y equals to 0, 0.2 plus 0.05 give us 0.25. And y equals 100, y equals 200, so on and so forth. We add them all together. Pretty easy, pretty straightforward, right? But that's a marginal probability mass function. Two things to remember. One, when we talk about a mass function, probability mass function, that's for discrete event, a discrete random variable, right? So they're discrete values. And two, for each marginal probability mass function, I don't know if you noticed here or not, at px, the sum of px equals to 1, right? The sum of py equals to 1 as well, right? So for each marginal probability mass function, the sum of all these probabilities together, you need to equal to 1 as well. Which, if we look at this table, it's pretty straightforward, right? Each time we calculate, no matter we count x, we have two rows, and one row, two row. This covers all the cells, right? Same thing for y. Y, we count different columns, but if we count all of them, that covers all the cells as well. So important, right? So to make sure that your marginal probability mass function, the sum equals to 1 as well. If you get some value that doesn't equal to 1, that means you made some errors, you made some mistakes. You need to go back and check your math again, right? So that's marginal probability mass function. Then, for the we talk about the discrete random variable. Now we of course going to talk about continuous random variable, right? So pretty similar and pretty similar to what we discussed about the probability density function for one random variable. Here we are dealing with two, right? One is capital X, the other is capital Y. They're both continuous random variable. Here, fxy is a joint probability density function for x and y. If for any two-dimensional set A, pxy belongs to A equals to integral and another integral on the entire A, right? On the entire A. Of the double integral on this fxy, then that gives you the probability, right? That gives you the probability. This pretty much says, right, there's x and y form one, both x and y determine an event or a set of events, right, for A. And that, of course, can easily draw a similar comparison to a two-dimensional rectangle, right? So basically, if A is a two-dimensional rectangle, x and y, for x, it needs to be between A and B, and y between C and D, then the probability for x and y just equals to that, right? The probability equals to from integral from A to B, that's for x, right? And then another integral for C to D, that's for y. Apply that to the entire probability density function, you get the probability, right? You get the probability. And that's how we define it. I mean, it's really, really like what we did before, right? For one random variable. Before you have the integral for fx dx, that gives you the probability, right? Here it's basically the same thing. Really, it's basically the same thing, right? You just do it twice. First time you ignore y, do the integral, and then after that you do the integral on y, right? You probably did this many times already. Now, here's the question. What is the probability, right, for all xy, fxy? So we do the integral on all the xy, all the space, all the rectangle together. What will that give us? What will be the probability? Think a little bit. Maybe you can pause the video as well. Think a little bit. Yes, it's equals to y for sure, right? Again, discrete or continuous, one random variable or two random variable doesn't matter as long as you cover the entire space. That gives you a probability equals to 1. No, definitely that's for sure, right? Definitely give you the same results. If after integral for all the areas, your probability doesn't equal to 1, that is something wrong. You need to go back and check the values, right? Now, if, like we said, if we think it is on a rectangle, right, then you can think this as continuous random variable, right? This figure here basically shows them a multivariate normal distribution, right? You can see that on X, there's two dimensions. Well, two dimensions of events, or there's two random variables. So on the independent variable space, it's basically a two-dimensional one, right? Both X and Y. And then the probability density function is basically shows as the curve on top, right, on the third dimension. But if you take slice, right, if you take slice at any value of X or Y, we'll talk more about this later, but if you take a slice on any of the value at X or Y, that gives you a normal distribution. That can always give you a normal distribution, right? So that's basically how the probability distribution looks like. That is, like, again, this is for a normal distribution. This is basically two variate normal distribution, right? So the total area of all the curved area on top of the blue area, the surface, basically, you integrate all of them together, that gives you 1, right? The probability equals to 1. That's for the normal, right? Multivariate normal distribution. But then more generally, it's probably something look like this, right? A, you see the shaded area is A. That's for independent variables, right? Basically for that, X is from A to B and the Y is from C to D, right? Then you do the integral on top of that. You basically find the surface, which is here, right? The area is here, but above it, the area is shaded area is here, right? But above it, this is the surface, and we are basically trying to calculate the area of this surface, which give you the probability, right? Basically give you the probability. That's how we calculate the probability for the two continuous random variable. This can be generalized to many other random variables as well. Same thing for the continuous random variable. There's marginal probability density functions. It's basically the same concept we did with a marginal probability mass function. So the marginal probability density function, like we said, is fx equals to the integral from negative infinity all the way to positive infinity for that, density function fxy, but we only do the integral for y. We only do the integral for y, right? So think this as, we set for an x value, and then we add all the y value together. Integral is basically a fancy way of sum, right? Basically, you can think it as a fancy way of sum, which is exactly what we did for the discrete random variable, right? We set for an x, we multiply all the y together, that give us the marginal probability density function for fxx. Same thing for fyy, right? You do the integral from x and y integral for x from negative infinity to positive infinity, but you leave y alone, right? You leave y alone. The same thing, remember what we did for the columns. We added the column together for the a discrete random variable. So here, again, it's a fancy way to do the sum, right? That can give us a marginal probability density function. Here's the summary. If we put them together, you can see this more easily, right? For discrete values, we have mass function. For continuous, we have density function, but they are paralleled, right? Here we have probability, here we have mass function. And then here we do two sum, but here we do two integral, right? Both of these ways give our total probability equals to 1. And for discrete ones, the probability equals to bigger or equal to 0 for any joint event, right? And then here, the density function is bigger or equal to 0 for any joint event as well. And the probability for event A is basically the sum of px, y, right? This is for all the x, y equals to A. You add them all together. And then for the continuous random variable, you just integral all of them together, right? That gives you the probability. And then marginal one, right? For discrete random variable, we add them together. But for continuous one, we do one integral on one variable. And that gives us a result. But it's, you can easily see the connections here, right? You can easily see the connections here. Okay, the last thing I want to talk about in this lecture is the independent random variables. So how to judge if the two random variables x and y are independent from a joint distribution, right? So here's the definition, basically aligned with what we discussed before. If there are two random variables, x and y are independent, then you have for the following conditions. So for discrete random variables, px and y for all the values equals to pxx multiplied by pyy. So basically, the joint mass function for all the value equals to the marginal mass function for x multiplied by the marginal mass function for y, right? So that's for discrete random variables. For continuous random variable, fxy equals to fxx multiplied by fyy. Then basically the joint density function equals to the marginal probability density function for x multiplied by the marginal probability density function for y, right? If any condition is not satisfied for all the x and y, then x and y are dependent. X and y are dependent, right? So that means for, let's say for discrete random variables, there can be many cases, right? Remember what we have before. For the marginal ones, we have the previous case, right? For here, we have the marginal mass function x, there are 2 values, and y, there are 3 values, right? So there are many cases. We only need to find one case that px multiplied by py does not equal to pxy. Then we can decide that these are not dependent. These are not independent, they're dependent, right? Of course, to prove that they are independent, that takes some calculation. We need to calculate all the combinations before we can say, okay, this is right? So let's look at this example. Actually, we're going to use the example we used before, right? We already have this, right? This is example we used, we have for the car, auto insurance, and home insurance, right? Now we need to find if X and Y are independent or not. X and Y are independent or not, right? So like I said, right, if we want to find independent, we need to calculate every one and then to make sure this is right, right? Otherwise, if there's any pxy does not equal to px multiplied by py, then they're not independent, they're dependent, right? So I'll give you a few minutes to calculate. You can pause the video, take a few minutes and calculate. Try if you can find if they're independent or not, then come back. Okay, so this is actually pretty straightforward, right? Like we said, if we want to, if we want to find out or prove they are not independent, we just need to find one case that does not support the independence, right? So basically, here's what I did, right? So you see that for P, X equal to 100 and Y equal to 0, that's this value, right? That is this value, which equals to 0.2, right? This need to equal to Px 100 multiplied by Py 0. And these two values are already given, right? This is this one, so Px 100 equals to 0.5 here, right? And then Py 0 equals to 0.25. So here, right? So multiply these two together, this gives us 0.125. And for sure, you can see that these are they independent? No, of course, they are not independent because these two values are not equal, right? So we know that they are not independent. So we prove that these two values are not independent, so we know X and Y are actually dependent. Here's another example. This is for a continuous random variable, right? You have two light bulbs. Let X equals to the lifetime of the first bulb and Y the lifetime of the second bulb, both in 1,000 of hours. So meaning if X equals to 1, that means 1,000 hours, right? X and Y, see, it's already said X and Y are independent. We know the independence already, and that each has an exponential distribution with lambda equals to 1. So I'm asking 4 questions. What is the joint probability density function of X and Y? What is the probability that each bulb lasts at least 1,000 hours? What is the probability that the total lifetime of the two bulbs is at most 2? And what is probability that the total lifetime is between 1 and 2, right? So this is a question for continuous random variable. I'll give you a few minutes to calculate. You can pause the video and take maybe 5 minutes or 10 minutes, however long you need. This one is pretty hard. Well, at least we never saw this before. So take your time and we'll come back to the question. All right, so let's do them one by one. The first one, right? What is joint probability density function of X and Y? Now, this two conditions already given, right? One is that X and Y are independent. The other is that each has an exponential distribution. So that's already quite some information. So here's the exponential distribution you already know, right? For a continuous random variable X, which has an exponential distribution, that means the probability density function equals to this. equals to this. This is from the previous slide, right? Equal to this. So now it's pretty straightforward, right? So we also know that lambda equals to 1, right? So we know we can write fx equals to e power to negative x, right? Fy equals to e power to negative y. So this is marginal probability density function for x and y. And we already know the independence, right? We know independence, which means this function holds. The joint probability density function fxy equals to the two marginal probability density function multiplied together. So fx multiplied by fy. And we already know fx equals to e power to negative x multiplied by fy equals to e power to negative y. So this two multiplied together equals to this, right? We know before that x, in this case, x needs to be bigger or equal to 0, and y needs to be bigger or equal to 0. So that's our joint probability density function. So easy to arrive. The second question, what is the probability that each bulb lasts at least 1,000 hours? 1,000 hours, right? So meaning that x equals smaller or equal to 1 and y smaller or equal to 1. Remember, each value 1 represents 1,000 hours, right? So that's what we do. So, here we say that each bulb lasts at most 1,000 hours. So both of them need to satisfy this condition. Then the probability basically is px smaller or equal to 1 intersect, right? This means intersect y smaller or equal to 1. Both of them need to happen. Again, because of the interdependence, we know intersection, right? Here means intersection, just equals to the probability of these two events. Oh. All right, here's this actually should be y, right? So, but basically px smaller or equal to 1 multiplied by py smaller and equal to 1, right? So this is probability. And remember, when we're trying to find the probability smaller or equal to something, we use cumulative function, right? Cumulative distribution. And for exponential distribution, the cumulative function equals to this. Fx equals to lambda e negative lambda x. But capital Fx, the cumulative function, equals to 1 minus e powered by negative lambda x. Lambda equals to x, lambda equal to 1. So that's why px smaller or equal to 1 give me this part. 1 minus e power to negative x, right? This is from cumulative function. Same thing for y. Again, this is y, right? Same thing for y. This should equal to 1 minus e negative y power to negative y. Both, in this case, x and y are smaller or equal to 1. We put the value in there, do the calculation. This gives us 0.4. This give us 0.4. Notice that this has nothing to do with what we learned today, right? I mean, yeah, it's related, but I mean, even from what we learned before, if there's independence between two events, then intersection just becomes the two probability multiplied together, right? We learned this before, and you see this rule holds for all the different probabilities, right? Even in this case. So that's how we calculate the second part. Now the third part, what is asking that what is the probability that the total lifetime of the two bulbs is at most 2? Meaning, light bulb A will run for a few hours and then burn out, let's say M hours, and Y will run N hours and burn out. But we want that the two parts modified together, that gives us at most, so basically M plus N smaller or equal to 2. Smaller or equal to 2. So the hour needs to be no more than, the sum of M and N, no more than 2,000 hours. And this is basically this, right? The probability of X plus Y smaller or equal to 2. We never dealt with this before. This is new to us, right? But this can happen for joint random variables, right? This is smaller or equal to something. So if we are doing smaller or equal to something, we always have, what do we have? We always have the integral, right? Use a cumulative function. So basically here we integral from, for this value all the way to 2, and then that is e negative x minus y dx dy. We just integral this together, right? Integral this together. Integral. Of course, this actually should be x plus y equals to 0, right? From 0 all the way to 2, what will be the result, right? So this, if you remember how we do calculus before, for this two variable joined two random variables, or just two variables in the calculus, this is how we do it, right? So basically, the maximum is x plus y equals to 2. Then y basically equals to 2 minus x, right? X plus y equals to 2. Then basically we move x to the other side, y equals to 2 minus x, right? Y equals 2 minus x. So basically what we are trying to do is that we first do the integral for y. See, I switch dx dy. I put dy in front. It's the same for x. It's just the way I choose to do it, right? I first do the integral for dy, and the range of y is from 0 all the way to 2 minus x. Whatever x is, the rest are for y. That's my range, right? Whatever x is, the rest, 2 minus x, is y. So that's from 0 to 2 minus x. Then, so I do the integral first inside this, for this part. Then I do integral for dx. dx is from 0 to 2. That's how we do it, right? Then I can do some conversion, make it into this. I basically just take the x out, because when I do y, I'm not doing nothing to x, right? I'm doing the integral on y, I'm doing nothing to x. I'm doing no operation on x. So I change it into this part. I'm doing integral for this part first, right? So this, when I do integral, it's become 1 minus e minus 2 minus x, right? Try this. If you have any questions, feel free to ask me on the Microsoft Teams classroom. I'm happy to show the procedure. It should be pretty straightforward, right? So I did this. Now see, in this formula, there's no y anymore. The only thing left is x. The only thing left is x, right? And x is from 0 all the way to 2, doing the integral, right? So this, I do some operation, make this formula a little bit, make the equation here simpler, and then do the integral. This give me 1 minus 3 e powered by negative 2, and do the calculation. It's basically give you 0.594. That's what we get for the third part. And the probability, so basically about 60%, right? The two light bulbs will both burn out before 2,000 hours of working. Right? So that's part C. And part D, and if we know how to do part C, then part D is relatively straightforward and easy, right? So it basically asks, what is the probability that the total lifetime is between 1 and 2? So this, again, so we are asking basically the probability of x plus y bigger or equal to 1, but smaller or equal to 2. And that, basically equals to whatever smaller than 2 minus then whatever smaller than 1. And then middle part is 1 to 2, right? We did it, then, we already calculated this, right? We just need to calculate this. And this is pretty straightforward. Well, not straightforward even, but very similar to what we did before, right? Just the top range, the maximum threshold only goes to 1. So we do this integral, that gives us 0.264. And then we put this value and then the previous value into this equation. So that's equals to 0.594 minus 0.264 give us 0.333, right? So that's the value, the probability of the two light bulbs last more than 1,000 hours, but shorter than 2,000 hours. That's basically the probability is 33%.